Okay, two questions have just been asked. The first is, how do we load and parse the data? Let me answer that really quickly. So in our assignment number 1, there was this starter kit, and I don't know if everybody looked around very much or just did the minimum necessary to complete this assignment. But in here, there wasn't a matrix class. I thought there was.
There was.
Oh, there was in the neural net class, that's right.
But it's in the JSON format.
If we look at the neural net class, there's a matrix in here. And the matrix, you want to look at Java or C++?
Right now,
They're almost identical. So in this matrix class, there is a load arf method. There it is. And if you call load arf, it will load the data set that I gave to you. I should have pointed this out before. I apologize, but basically here's a parser for you that will automatically parse all that data and hopefully save you having to write your own parser. So there's that. Well, to some extent I didn't point it out at you. To some extent you didn't look around at the code I provided. I don't know. Basically sorry, but that's how learning happens, is pain. Yes, I'm a professional torturer. Oh, sorry. The second question is, how am I grading this thing? So I gave you an algorithm and I gave you a data set, and truthfully I haven't tested this data set on this algorithm yet. So I was going to wait and see what results everybody get, and everybody that got about the same thing, I'll say they must have done it right, and then everybody else I'll say, hey, your numbers are way off. What's going on? Now, the reason I feel comfortable doing that is I've already split the data into training and test portions, right? So everybody should get exactly the same results, because if you're training on the training features, and then for each test feature you find the nearest neighbor in the training features, there is a nearest neighbor. There are 3 nearest neighbors in that space, and if you find different neighbors, well, you're wrong, right? Okay, so what can account for differences? So there's the way you do Hamming distance, if you divide by 2 or whether you divide by 1. So there's 2 clusters of results that we'll get right there based on how you normalize that. We are going to normalize all of the deviations by all the real values we're going to divide by the standard deviation, right? That's in the instructions. So yeah, if you go ahead and tune the weightings of the various attributes such that you get better accuracy, then that's awesome. That's going above and beyond what was required for the assignment. So I'm certainly not going to penalize you for getting better accuracy by doing that. Let's see. I'm pretty sure the assignment's deviation. Did I specify to divide out the deviation? Okay. When I say divide out the deviation of the continuous attributes, I'm saying use Mahalanobis distance. They're kind of the same thing. Now, Mahalanobis distance doesn't specify how to manage categorical attributes. And so I'm saying for categorical ones, let's use Hamming distance. Or if you want to use half of Hamming distance, I suggested that might be even better. So the assignment kind of says do that, which I think is pretty standardized. But yeah, if you went on and tuned your weights, that's awesome. That's a good point. I think that will change the results, and for that, I'll just have to deal with it. I guess it'll come down to me looking at your code and making sure you kind of did all the main points then. If you're getting terrible accuracy, I think this data set, if you're getting 1% error and 99% accuracy, and I don't know, I haven't tested, so I don't know if that number is right. But if you're getting something in that ballpark, you're right on. If you're getting something like 30% error and 70% right, then there's a bug in your implementation somewhere. And usually all the assignments fall into one of the 2 categories, so I don't have to spend a lot of time figuring out who has a bug and who doesn't. I'm just going to say if you get pretty good accuracy, you're probably right on. If you're getting perfect accuracy, you're nailing every single, everything in the test data, you're getting it exactly right. I'm scrolling down to look for the test data, but forget about it. That's also a bug because there's no way in heck you're going to get 100% accuracy. So you should get a few wrong, you shouldn't get many of them wrong, and then I don't think there's many ways to do that without doing it right, because that's the whole point of an instance-based learner. So if you achieve that, I'm calling your assignment good. Yeah, well, truthfully, I just pulled that number out of my head. I don't know what the number is right now. Somebody said they'd gotten accuracy. Anybody want to state the number?
35 misses.
35 errors out of how many are in, out of 1,000? 35 out of 1,000. Wow, that's pretty good.
I got 47.
47 out of 1,000?
Yeah.
Okay. So half of 1%-ish is about the target. And if you're getting in that range, I'm going to go with it. Because the last thing I'm going to do is dig through your code and start hunting for bugs for why you're missing two more, you know, two of them are off when you need to get those two right. But if you've got 25% of them wrong, I'm going to say, hey, you got a bug. Your problem now. Go deal with it. Oh, it's 5% error?
Yeah.
35 out of 1,000. Wow, my math.
That's 3.5%.
35 out of 1,000 is 3.5%. And 47 out of 1,000 is 4.7%. So, okay. You should be getting about 95% accuracy on this, ish. That sounds about right to me. All right, let's validate that just because we can. Data class UCI. Okay, what's the data set that I gave you? Was it
Medical data.
hepatitis?
Right.
Oh yeah, the hypothyroid.
It was hypothyroid? Okay, let's do that one. Hypothyroid. Okay. Waffles, learn, cross-validate, hypothyroid with KNN neighbors 3. So, I'm not doing exactly the same split that you're doing. I'm doing I'm shuffling the data and doing a random split. I'm using my k-nearest neighbor implementation with a KD tree. And so I'm chopping the data up into two splits. I'm training on one half, testing on the other, then training on the other half and testing on the first half. This is called cross-validation. I'm doing 5 repetitions of twofold cross-validation. I'm getting 5.2% misclassification rate and nearly 95% accuracy. Now what I did for the data I gave you is I took the same data and I shuffled it and I split it into 2 parts, training and a test set portion, and I zipped them up and gave them to you. Now I don't know exactly which parts I did. I could test that right now and find out if I cared, but this number matches what you guys have just told me, so I'm going to say if you get about 95% plus or minus a few percents, you're right on. If you're plus or minus 10% there, there's a problem. Is that enough clarity?
Yeah.
Okay. Just out of curiosity while we're doing it, let's try a decision tree. Much faster, but not as good of accuracy. Let's try a bagging ensemble of 100 decision trees. Still not as good as KNN. That's interesting.
Can you do a neural net?
Let's try bagging ensemble 100 decision trees with random divisions. This is random forest. Oh, what's the problem? Oh, that's because I needed to specify the number of random attributes. Random forest does a little bit better.
About K&N.
That's about the same as KNN. That's interesting. Let's do naive Bayes just because we can. It's 93% accuracy. Well, that's kind of validating to know that KNN is one of the better models for this particular data set, especially since I used it to test your KNN implementation. So, yay, that makes you feel good. All right. Oh, the one thing I did want to say, though, is one thing that will not affect your accuracy are the differences in how you choose to split divisions in your KD tree, right? I think I've kind of hammered that in. But if you decide to go with the median rather than the mean when building your KD tree, that's one thing that shouldn't affect your accuracy because the KD tree exists for only one purpose, and that's to speed up your finding of neighbors. It shouldn't change which neighbors you find, no matter how you implement it, unless you have a bug. I'm not sure I understand the question. Here's what I got. If we normalize the data based on the deviation in the training set, how does that differ from, or how does using the Mahalanobis distance differ from first normalizing the data and then using the data? Is that the question? Okay. Mahalanobis distance says, measure the distance as if you had divided out, or measure the distance and then divide out the deviation. And an alternative is you could take your data and you could scale out the deviation, and then you could just use plain old Euclidean distance. Or you could use Mahalanobis distance if you wanted, but it wouldn't do anything because the deviation would always be 1. I claim they will be identical. So there's absolutely no difference between doing the two. Here's why. Math. I mean, it's divide now or divide later. Either way, you're dividing by the same number. You still get the same number, right? So if you divide out all the deviation from the data itself, 1, you kind of screw up your data, which makes you feel bad. And 2, but then you don't have to worry about it later when you calculate distances. I really don't think there's any difference there. It's just dividing out by the deviation, so shouldn't make a difference. All right. Sorry, I'm a little slow on my mouse today because I have to use my touchpad. I left my mouse at home. And I closed my window. Why did I do that? And the internet is down, so I have to open it manually. Fortunately, I have a cached version on my computer. Okay. Assignment 4. So we have talked about finding the first principal component. Last time we did the Gram-Schmidt process, and then we talked about principal component analysis, which basically means find the first several principal components and use those to reduce the dimensionality of the data. So far, how are these concepts sticking to you? Do you see how to do it and even why it would be a useful thing to do?